Good morning and welcome to the lecture series of numerical analysis. In the last lecture, we drive and discuss Newton's forward and backward interpolation formulae, which are applicable for interpolation near the beginning and end respectively of tabulated values. We shall in the present section discuss central difference formulae, which are most suited for interpolation near the middle of tabulated values. The central differences formula was given by Gauss, Stirling, and Bessel. So we will derive these formulas one by one. So first we derive the Gauss Forward Formula. Now we consider the difference table 1.4, which is the central ordinate, in which the central ordinate is taken for convenience as y0 corresponding to x equals to x0. It means these are the given ordinates and the corresponding arguments are given. So for the convenience, we have used x0 as the central value of the given data points. Corresponding left values are denoted by x suffix minus 1, x suffix minus 2, x suffix minus 3, and right side values are represented by x1, x2, x3. Similarly, corresponding argument values. So for the convenience, we have used center as x0 and corresponding argument is y0. So first we try Gauss forward formula. So in this we start with the first forward step from y0. Now if we take the first forward step, then we get del of y0. And then now next we take the backward step. It means del to y minus 1. Now next we take forward step, which is del to y minus 1. Now we take del 4 y minus 2 backward. Now next one is forward del 5 y minus 2 and backward del 6 y minus 3. Correspondingly, we find the higher order terms. So in Gauss forward formula, we start with y0 taking first step as forward, while in case of backward formula, we take the first step as backward step. It means del of y minus 1. So by using these steps, first we try Gauss forward formula, so we take first forward step, then backward, forward, it means alternative steps, forward, backward, forward, backward. So y0 is our central point. So we take first forward step. So by using these values, let us assume that our formula is of this form: yp equals to y0 plus z1 del y0 plus z2 del 2 y minus 1 plus z3 del 2 y minus 1 plus z4 del 4 y minus 2 and so on. Here g1, g2 are unknown, which we have to determine. To determine these unknown g1, g2, we express this left hand side of 1.5 in terms of y0 and forward differences of y0. It means y0 del 2 y0 del 2 q y0 del 4 y0. And expressing these higher order differences del 2 y minus 1, del q y minus 1, del 4 y minus 2, del 5 y minus 2 in terms of the y0 and del of y0 and higher order differences of y0. So basically, we derive these unknown coefficients z1, z2, z3 by expressing the left hand side as well as right hand side in terms of y0 and higher order differences of y0. So how we do this? So first we express this left hand side yp in terms of y0 and del y0 and higher order differences. So we know that yp can be written as e raised power p y0, where e is our shifting operator, and we know that relation between shifting operator and forward difference operator, which is p equals to 1 plus del. So 1 plus del k power p over y0. If we use the binomial expansion here, then this can be written as y0 plus p times of del y0 plus p into p minus 1 upon 2 factorial del 2 y0 and so on. This is our left hand side now, yp equals to this term. Now similarly, the right hand side of the equation 1.5 can be expressed in terms of y0 del 2 del of y0 and higher order differences of y0. It means you could see here that first and second terms are in terms of y0 and del of y0. Third term del 2 y minus 1 we have to express in terms of y0, del of y0 and higher order differences of y0. So this del 2 y minus 1 can be written as del 2 y minus 1 can be written as del 2 e raised power minus 1 y0. Here e is our shifting operator. So this can be written as 1 plus del t power minus 1 y0 by using binomial theorem. So this can be written as 1 minus del plus del square minus del cube and so on y0. If we operate y0, then we get del 2 y0 minus del 2 y0 plus del 4 y0 minus and so on. Similarly, del q y minus 1 can be written as in this form. Del 4 y minus 2 can be written in this form. So hence equation 1.5 gives the identity. It means if we substitute the derived values in equation number 1.5, then our left hand side is y0 plus p times of del y0 plus and so on. Similarly, y0 plus z1 del y0 and so on. Now, if you compare the values of corresponding coefficients, it means coefficients of y0, del of y0, del 2 y0 and so on. Now, the coefficients of del y0 gives the value of z1, coefficient of del 2 y0 gives value of z2 and so on. So now if we evaluate this is after some simplification, we get this relation 1.7 by comparing the both sides. So we get yp equals to y0 plus p times of del y0 plus p into p minus 1 upon 2 del y minus 1 plus and so on. So this is our Gauss forward formula where p equals to x minus x0 upon h. Now this formula is applicable when we are interested to find the value of the interpolating polynomial to the right of the center point. Right? Similarly, if we are interested to find the interpolating polynomial to the left of the center point, then we use Gauss backward formula. Same procedure we have to apply. The difference using this table are defined in table 1.5. The Gauss backward formula is therefore of the form yp equals to y0 plus p times del of y minus 1 plus p plus 1 upon 2 factorial and so on. Because why it is so? In case because you could see here, because in case of Gauss forward formula, we start with center point y0 and take first step as a forward step del of y0. While in case of Gauss backward formula, we take the first step as a backward step. It means del of y minus 1 over first term. Now next step is forward, next is back, next is forward, next is back, next is forward. So our backward formula start with del of y minus 1, while our Gauss forward formula start with del of y0. So this is our Gauss backward formula, where p equals to x minus x0 upon h. Here h is the step size. It means differences between corresponding coordinates. It means values of x. Now here it is convenient to start with x0 nearest to the x and then introduce x minus 1, x1, x minus 2, x2 and so on. It means if we are interested to find the value of x near the center point, then we define the nearest to the x. For example, find the value of e to the power 1.17 using Gauss forward formula. Now here we could see here that 1.17 is close to 1.15. So we take x equals to 1.15 as a x0. Alright, so this is our x0 point now. This is our x0 point, and this is our x minus 1, x minus 2, x minus 3, and similarly right hand point is x1, x2, and x. These are the values of the corresponding values of e to the power x. So we took x0 as our center point. So this is our corresponding y0. Now we are using Gauss forward formula. So we take first forward step. This is our first forward step, which is del of y0. Now we take backward step. This is del 2 y minus 1. Next we take forward step. This is del cube y minus 1. Next backward. This is del 4 y minus 2. Now next forward del 5 y minus 2. Next backward del 6 y minus 3. Right? Now we have x equals to 1.517 because we are interested to find the value of e to the power 1.17. So here x equals to 1.17 and x0 is 1.15 plus p, and h is the step size. It means difference between corresponding coordinates, which is 0.05. Now if we simplify, then we get p equals to 2 upon 5, which is 0.4. Now using Gauss forward formula, which was given in 1.7, we have this relation right? Now if we simplify this, and then we get 3.3, 3.2221. Now next we derive Stirling formula. Now if we take the mean of Gauss forward and backward formula, which was given in equation 1.7 and 1.8, we obtain this relation 1.9, which is known as Stirling formula. So basically your Stirling formula is the average of Gauss forward as well as Gauss backward formulas, right? Similarly, one could define the Bessel's formula, which is very useful for practical interpolation and is given as yp equals to y0 plus p del y0 and so on. Now, practical interpolation, it means which formula is we have to use for the particular interpolation. It means in the preceding sections, we have tried some interpolation formula of greatest practical importance. And natural question is which one of these formula gives the most accurate result of the interpolation. Now, first one, for the interpolation at the beginning or end of a tabulated values, Newton's forward and Newton's backward for interpolation formula have to be used. It means if we are interested to find the interpolating polynomial value of the interpolation near the end of a table or near the beginning of the table, then we have to use Newton's forward or Newton's backward formula. Now, for interpolation near the middle of the set of values, the following are the choices. It means Stirling formula is applicable if our p lies between -1/4 up to +1/4. It means this formula, Stirling formula, gives the best result if p lies between -1/4 to +1/4. Now, if p lies between 1/4 to 3/4, then this Bessel formula gives the best interpolation result, right? So let us see one example based on Stirling formula. So using Stirling formula to find the value of y at x equals to 32 from the given table. Now here x equals to 32. So it's our choice. X0 is center point. Here 4 points are given. So since x equals to 32 lying between 30 and 40, so we take x30 as the origin. So we take this is our x0. And this is our corresponding y0, and h equals to 10 because differences between the corresponding ordinates are 10. So therefore p equals to x minus x0 upon h, which is 0.2, which is less than 1/4. It means p lies between -1/4 up to +1/4. So we apply Stirling formula, and this formula will give the best result for the interpolation. Hence we apply Stirling formula. So the difference table is given by this one. This is our x0, this is our y0. So keep in mind here that in case of odd differences, we take the average of differences. It means here del ki power 1, so we take the two differences, -73 and -93, and take the average of this one, and -20. In case of del 3, it means in case of Stirling formula, we take the averages of the odd differences, while in case of Bessel formula, we take the averages of the even differences, all right, in the formula. So you could see here that this is our odd differences, so average of odd differences. This is our odd differences, is average of odd differences. So in case of Stirling formula, we take the averages of the forward differences, while in case of Bessel formula, we take the averages of even differences. It means del ki power 4, del ki power 2, del ki power 6, and so on in the formula. So if we put the values, corresponding values of y0, del y0, and other differences in this Stirling formula and simplify, then we get this value y at 0.2. Here p is equal to 0.2, which is 422. So value of the interpolation at x equal to 30 is 422, which is our required result. So thank you for today.